Hello everyone. Let's review this very important property, and it has a lot of application. So if you have a signal x of t, and that's the Fourier transform, what happened when you multiply this signal by this exponential? You are basically shift the spectrum of x of t, which is x of omega, to be centered around this frequency. So it will be x of omega minus omega 0. So if x of omega looks something like this, and I multiply the signal the time domain by this one, now the spectrum, this spectrum will be centered around omega 0, and it will look exactly like this. So you shift the spectrum to be centered around omega 0. Now with this property, we can find what happened if I multiply any signal x of t by a cosine omega 0 t. Well, this is the same as x of t multiplied by half e j omega 0 t plus e minus j omega 0 t. And if I need to find the Fourier transform of this function, it will be the Fourier transform of half, which is a constant, comes out, x of t multiplied by this ej omega 0. We use this property. So it will be x of omega minus omega 0. We still have this quantity. X of t multiplied by this quantity, we're going to use this property. But instead of omega 0, now it is minus omega 0. So it will be plus x of omega minus omega 0. And when you multiply minus minus, you get plus. So this is this property. And this property says the following. If you have a signal x of t and you multiply it by cosine omega 0 t, you basically shift the spectrum of x of t to be centered around minus omega 0 and plus omega 0. If I have the spectrum of x of omega, a speech signal, that probably looks like this. When I multiply the speech signal by a cosine of high frequency, omega 0 could be 2 pi a million hertz or 2 pi 100 million hertz. That means this spectrum will be centered around omega 0 and minus omega 0. So you shifted the original spectrum to a higher frequency range. And this is amplitude modulation. It's just like the AM. You listen in the radio, AM, FM. FM is frequency modulation. AM is amplitude modulation. Our speech has small frequency content. So if I need to transmit it, I need a long antenna. So what we do, we shift the speech spectrum to a very high frequency, like 100 megahertz. When you listen to 98.1 radio, you are shifting the spectrum to that 98.1 megahertz. So now I will need a very short antenna to transmit this wireless or radio frequency. And this, we call it amplitude modulation. So when you have a signal x of t and you multiply by a cosine omega 0, that's amplitude modulation. X of t is the message signal. Cosine omega 0 t is the carrier. The whole thing here, we call it the modulated signal. If that is your signal, let's say a portion of your signal, this is time. After you multiply it, ignore the green things. So after I multiply it by cosine omega 0 and omega 0 very high frequency, then we will get this. And the red thing is what you will be transmitting through antenna, radio frequency or wireless. Where is the message? The message is in the envelope. So at the receiver, they extract the envelope, they extract the message, and we will see how they do that. And that's the importance of amplitude modulation. Let us take an example of amplitude modulation. So let's say you have this signal. So you have a rectangular of width 4 with amplitude A and width 4 multiplied by cosine with frequency 10. And we need to know what's the Fourier transform. of this signal? Well, we can think of it in terms of amplitude modulation. We can think of this as x of t modulated by cosine. So it will be the spectrum of x of t, which is x of omega, and from the table we know a rectangular has this Fourier transform. If I call this x1 of t, so x1 of omega will be a, the amplitude, and the Fourier transform of a rectangular function is tau sinc omega tau over 2. In this case, tau is 4. So that will be time 4 sinc 4 omega over 2. So this is the Fourier transform fx1 of omega. And if we plot these, it's going to be a sinc function like this one, with amplitude 4a. x1 of t multiplied by the cosine 10t, the Fourier transform of this whole thing will be the sinc function centered around minus omega 0 and plus omega 0. X of omega, the Fourier transform of the whole thing here. It will be the Fourier transform of the rectangular function, which is 4a sinc 4 omega plus 10 divided by 2 plus the whole thing shifted around minus omega 0. So that will be 4a sinc 4 omega minus 10 over 2. And everything multiplied by the half. You can clean this a little bit, and x of omega will be, and that's the Fourier transform. So basically it is a sinc function centered around minus 10, another sinc function centered around positive 10 with amplitude 2a. So we started with a message signal, which is a sinc function amplitude 4a. We end up with, because of the amplitude modulation or multiplying by these, we shifted the spectrum here to be centered around 10 and minus 10. A big application of amplitude modulation is in wireless communication or transmission through radio frequency. And this is the transmitter. And how does it work? Very simple. You have a message signal m of t, and that could be speech. And speech, the highest frequency is 20,000 hertz. There is no way we can transmit this in radio frequency or wireless. 20,000 hertz, the wavelength is lambda equal c over the frequency. C is the speed of light, 3 times 10 to the power of 8. And the frequency, the highest frequency in speech is 20,000 hertz. So we're talking about 1.5 times 10 to the power of 4, the wavelength. You need an antenna at least half the wavelength. That's 15 kilometers. So you need an antenna 7.5 kilometers, which is impossible to build. So then what's the solution? Even if I take the lowest frequency, which is 200 hertz in speech, that even will need a longer antenna. So how we deal with this problem? Well, we deal with it amplitude modulation. We shift the spectrum of the speech to a higher frequency band, like around 100 megahertz. Now we will need a smaller antenna, maybe a meter or even centimeter, to transmit the signal. And that's exactly what they do. When you hear in the radio in your car, AM, you are hearing amplitude modulation. FM is frequency modulation. So how does it work? At the transmitter, they take the message signal, m of t, they multiply it by a carrier, that could be 100 megahertz. So then you will get, this is the signal you will be transmitting. And that will be the modulated signal, m of t cosine omega ct. So that will be this one here. So then you take it through an antenna and you transmit it. If you look in the frequency domain, if this is your part of your message signal and it has this spectrum with a band 2 pi b, b could be 20,000 hertz, And when you modulate it with cosine omega c, you're taking this spectrum and you center it around omega c and minus omega c. And omega c is like 100 megahertz, so now you need a small antenna. So you transmit this signal. Now the question is, at the receiver, like your cellular phone or your radio in your car, how do you get from this signal? This you will not even hear it. It's beyond our hearing ability. How do you get back the message signal, this one, m of t? So let's look at the receiver and look at amplitude demodulation. Amplitude demodulation work as follows. So this is the receiver. You will have like an antenna here picking up this signal, and then you multiply it by the carrier here, cosine omega ct at the receiver, and what you will get, m of t cosine omega ct, that's the received through the antenna. Then I multiply it by this, so time cosine omega ct, so that will be m of t cosine square. And I can use trigonometric property and break the cosine square to the following. And this is just half m of t, half plus m of t times half times cosine. So this is the signal here, which is the same as this one. But now, when you look at this one, this is our message signal. How do we get rid of this? If we look in the Fourier transform, it's easy to figure out what's the next step. Because if I plot the spectrum of this signal, I get the spectrum of half m of t gonna be, let's say, something like this. This is the spectrum of this part. Now the spectrum of this one will be again the spectrum of m of t, but centered around 2 omega c and minus 2 omega c. So it will be here 2 omega c and minus 2 omega c. So if I want to hear the message signal alone, that means I have to filter out this. And how do I filter out this one? Well, I take it through a low pass filter with a cutoff frequency here, omega c, much less than 2 omega c. So these will not pass through the low pass filter, which is this one. And what you get out of the low pass filter, only this portion. And that's how we do amplitude demodulation at the receiver. The only challenge is the following. That means at the receiver, you have to have this carrier. So if there is a Doppler effect during the transmission of this one and omega c is shifted, now when you do this multiplication, this won't be any more omega c. It could be omega c plus 0.01 hertz. So then this, actually you will not get it, and you will get m of t with some distortion cosine function. So how do we resolve this problem? How do we get over this? Well, we use amplitude modulation again, but first we shift up the message signal, and that's something like this. So I take the message signal. Usually the message signal will have positive component and negative component. So I shift it up so there is no negative component. So I add to the message signal a plus m of t, such that a plus m of t larger than 0. There is no negative, so that will be the signal. Now I do amplitude modulation. I multiply it by cosine. So when you do this, then that will be the signal, the modulated signal. Now your message signal, this one, is hidden in the envelope. So when you transmit this signal at the receiver, all you need is a full wave rectifier. You don't even need to know what's the carrier. All you need is you take this black signal and you do a full wave rectifier. So that will be then like this after the full wave rectifier. And then you use low pass filter. Low pass filter that will, the time constant is large, so it cannot follow this fast fluctuation. Only it can follow the envelope of the message, and that will be the message signal. what you are gaining, the receiver doesn't need to have the carrier. So that's a big gain. But what's the price we are paying for it, for this advantage? We are transmitting A time cosine omega ct. See, I'm modulating this whole thing. So that means I will be transmitting A cosine omega ct plus m of t cosine omega ct. So I'm transmitting this signal in addition to the message signal. So that is a power loss, and that's the price we are paying. Now with amplitude modulation, we can use frequency division multiplexing. And how does it work? Let's say you have many messages you are trying to transmit. You are trying to transmit M1 of t, M2 of t, Mn of t in the same cable, in the same medium. That could be a coaxial cable or optic filter or over wireless. So how do we separate them such that at the receiver they will be able to pick up the message they are interested? Different party or different company will pick up the message that belong to it. Well, we use amplitude modulation. You take message 1, you do amplitude modulation with a different carrier, omega 1, that could be 100 hertz. So the spectrum at this point will be this. Then you take message 2 and you multiply it by cosine omega 2 t, different carrier, and you add it with this. Yes, in the time domain, when you add them, they will look garbage. You will not even hear it, and very difficult in the time domain to separate them. But in the frequency domain, they are separable because the spectrum of this here will be this. So this is the spectrum of message M2, but it's centered around the carrier omega 2. This is the spectrum of message 1 centered around omega 1, and so forth. So even though you add them here, and in the time domain, it's impossible to separate them, but in the frequency domain, they are existed in different band. So they are still separable. Then after you do that, you do another amplitude modulation. So then you multiply the whole signal here by a cosine to 1 gigahertz. So you shift the whole spectrum here. Now it's gonna be way here. It could be 1 gigahertz. So what you are getting this one, and so forth. And then you will have this replica in the negative cycle. So this is a new carrier, and you transmit. At the receiver, different city, it will pick up, it will do demodulation, so it will multiply by cosine, like if this is like omega c, the carrier, it will multiply by cosine omega c. So it's gonna shift this spectrum back to here. Then it will take the whole signal here and do demodulation or a band pass filter to separate omega 1, to separate this by itself out and eliminate all these. Then do demodulation. You multiply by cosine omega 1 to bring this back here. So then here you will get this signal here to be here. And that's your message signal. And in this, after the band pass filter, you will get this signal. This is omega 1. And those will be filtered out. And when you do demodulation, you will center this back again here, and you get your signal. Same thing for omega 2, a band pass filter. This will be the band pass filter. So it will filter out this out, and this out, and this out. And the signal here will look something like this. Then you do demodulation. So the signal here will look something like this, which is your M of t, and so forth. And that's frequency division multiplexing. That means you are transmitting many messages in the same medium, coaxial cable or fiber optic, but they are located at different band. Just like if you are in a neighborhood and there is 100 house AT&T and they are going through a same cable, but every house the message, whatever video or wireless or cable, it will exist in different bands of the spectrum. All right, this is a big major application of amplitude modulation property of the Fourier transform. Next concept is energy of a signal that eventually die out. And we already learned how do we calculate the energy in the time domain. It just, you take x of t, you find the magnitude, you square it, and then you take the integral. Now, I can calculate the same energy of the signal in the frequency domain. So if I have x of omega, the spectrum of the signal, and it could look something like this, the magnitude, I square it and I integrate. So I will find the area under x squared omega, and then you divide by 2 pi, and that will tell you the energy of the signal. Now, because x of omega is always the magnitude gonna be even function, so that means this area gonna be exactly like this area. So I can simplify things and say the energy, instead from minus infinity to infinity, I will integrate from 0 to infinity and multiply here by 2. So when I multiply here by 2, it will be 2 divided by 2 pi, I get 1 over pi. And that's an easier way to find the energy. Let's take one important application of this energy, which is this example. You have a signal x of t which is e minus a t u of t. If we plot it, it will look something like this. And we want to find how much of the frequency I need to keep in x of t and how much of the frequency I can delete. And there is one criteria to decide how much do you keep and how much do you delete. Maybe I want to delete because to save storage or to make a transmission faster, or because I don't need larger channel bandwidth to transmit the signal. So how much high frequency I can get rid of without affecting the shape of x of t. One criteria to decide is keep up to frequency, let's call it omega 0 or omega c or omega a, such that you still have 95% of the energy of the signal. So the frequency, the high frequency you will delete is only worth 5% of the energy of the signal, and we can tolerate that. So then how do we find that frequency omega, the cutoff frequency? One way is to find x of omega. So if we find x of omega, we can use the table, x of omega from the table. And if I find the magnitude, and if I plot it, this is omega, here it's t. When omega is 0, this is 1 over square root of a squared, so this is 1 over a. So now the question is, where is that frequency, let's call it omega c, such that, and let's call here minus omega c, such that the energy here, so we need to find this omega c. So how are we going to solve this problem? Well, let's find the total energy first. Well, the total energy of the signal, and it's easy to find it in the time domain. It's from minus infinity to infinity. So the signal in the time domain exists from 0 all the way to infinity. So that will be the integral from 0 to infinity. And this signal is just e minus a of t. The magnitude, it's not complex, so it's the same, the magnitude. You square it. So that is 0 to infinity e minus 2at dt, and when you integrate this, you should get 1 over minus 2a from 0 to infinity. And when you evaluate, when t infinity, this go to 0. When t is 0, that go to 1. It will be 0 minus 1 over minus 2a. So the total energy will be 1 over 2a. Okay, so we found the total energy of E of x. Now I need to find 95% of the energy, and I need to find omega c. So now I will calculate the energy in the frequency domain. So I'm gonna say the energy of the frequency domain, and we will use this definition. So the energy of 95% of x will be 1 over pi from 0 to omega c. Not from 0 to infinity. From 0 to infinity I get 1 over 2a, but to omega c of the magnitude square. We already found the magnitude here. So if I square it, that will be 1 over a square plus omega square, d omega. And these should be 95% of the total energy. So 95% is 0.95 of the total energy, 1 over 2a. Now you carry out this integration, and you can use the integration table to find the integral of 1 over a square plus omega square. And you should get, so in the integration table you have this integral. In our case, this integral here is exactly the same as this integral, except instead of x variable we have omega variable. So the integral will be 1 over pi 1 over a tan inverse omega over a, evaluated from 0 to omega c, equal 0.95 over 2a. And further, this will be 1 over pi a tan inverse omega c over a minus tan inverse 0 over a is just 0. This equal 0.95 over 2a. One further step, it will be tan inverse omega c over a equal 0.95. The a here will cancel the a here. So 0.95 pi over the 2. And if you take the tan of both sides, then you will get omega c over a equal tan 0.95 pi over 2. And omega c will be a times tan 0.95 pi over 2. So now you use your calculator. Find the tan of these 0.95 pi over 2, and you should get 12.7 and multiply it by a, and that's omega. So you have to keep up to 12.7 a radians per second. Anything above this frequency you can eliminate it. A will depend on this one. So if A is large, then you have to keep more frequency. But what does it mean A is large in the time domain? That means the shape of x of t will be even very fast decay if A is large. A very fast decay means the frequency has to be large, because the rate of change depends on frequency. If the rate of change is very large, that means the signal change very rapidly. It means it has high frequencies. We covered all these Fourier transform property in the time domain and the corresponding property in the frequency domain.